What is going on, arcade? Someone asked me to do a video that just explains some of the basics of how to repair a circuit board. Now, I really can't tell you everything there is to know about how to repair a circuit board in one video. So this is what we're going to do. We're going to keep everything basic, and I'm going to tell you the things, maybe or maybe not, in order that I would do when it comes to repairing a circuit board. Now, it just so happens I have a circuit board right here that was sent in for repair. And let me tell you step one. Step one, when you get an unknown circuit board or a known not working circuit board, what the first thing you want to do is clean. Clean, clean, clean. You want to make sure every socket looks nice and clean underneath these chips. You want to pull the chips and look at the legs of all these sockets, of all these chips. Now, let me show you something. I have 3 different types of chip legs right here. Okay? Here we have a lead alloy. Now, these are all steel pins, but here we have a lead alloy coating. And here we have a gold alloy coating. And here we have a silver alloy coating. Now, all of these can rust. Okay? If the coating were to be scratched, all of these can rust. And then rust is a whole different issue. Okay? But cleaning methods, my cleaning methods for each of these is different. Okay? Everyone says, first off, a lot of people say use a pencil eraser. I really don't like that idea. I never use a pencil eraser on electronics. I think it's Bush League. Okay? What I'll do is I will get a fiberglass pen. Okay? And I'll clean this with fiberglass pen. I'll clean this with fiberglass pen. But the silver alloy, I do not use fiberglass pen. You can. But what I do with the silver alloy chips is, and by the way, fiberglass pen will work. But what I do with this is I get Tarnex. See, this is a silver alloy, right? I use Tarnex in a little cup. I will put the chip in the cup, and or just have a little cup and dab a paintbrush in there, and brush it back and forth. Flip it over, brush it back and forth, and then rinse it off. It's that quick, and it is way shinier. It didn't remove any of the coating that you would if you were to scrub or sand. Never use sandpaper on your chips. People do it all the time. Don't use sandpaper on your chips. All you're doing is removing the electroplated coating that protects the steel so it can rust even worse in the future. So try to stay away from sanding, and that's partially why I don't like fiberglass, why I don't like pencil erasers, because you're basically sanding it. And you're a little rough. I mean, kind of rough on those pins when you're using a pencil eraser. It pulls the pins back and forth. Now, that's my preference. You can do whatever you want. Go down and yell at me in the comments, because there's a million different methods, a million different ways to skin a cat. But I don't like being too rough with these chips, and I don't like removing any of the protective finish, or removing as minimum amount as possible. But okay, so first things first, you got to clean your board. Make sure all connections are good and clean as possible. Now, prove it. How do we know those connections are clean? Well, one thing that's kind of nice is many like chips in a row are in what we call banks. Okay, and when a chip is in a bank, often the same pins will be shared with one another. So, for example, I have some EEPROMs here. If I were to get my probe, let me turn my meter on. Okay, so I have my meter right here, right? Open, short. If I were to measure this pin right here, I can go on the line. We have a short. That's good. We have a short. That's good. 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 So, what did we just test? Well, we tested the connection from the socket, from the chip to the socket, through the board, back to this other pin again. Okay? All the way across. Okay? So, that verified that we have a good clean connection from the chip to the socket. That also verified that the wire that connects from here all the way across is good. But there will be situations where, most likely around here, here we go. Well, some of these. There will be a few pins that do not connect. Okay? These are not connecting across the board. And that's okay. They're going to be going across to somewhere else. But we can still test about 95% of all RAM chips pin legs, of all ROM chip pin legs, and so on. We can actually test them and test the continuity between the chip and its socket by literally moving down the line. See, we know all those connections are good. Now, do you have to do this? No, you don't. But if you don't know much else, I might suggest it, because something like this can be found out later with a probe. Now, let me grab my probe. Okay, so first off, we're talking about clean connections. Okay, so we know we have clean connections at some point once you test everything. Okay, what I like to do is I use my probe, and when you use a probe, you have two connections here. By the way, these probes are cheap. Okay, I'm going to connect one to ground. I'm going to connect one side to 5 volt. Boom. Now, what you want to do is, let's say just to start off with, the CPU side does not work. You have nothing on the screen, you have no idea what's going on. What I suggest doing is, what I usually start with is the CPU. Okay? Now, you can look up different data sheets. You can look up, for example, we have a 6502 processor, 6502A. Okay? And in this situation here, if you go on Google and type in 6502 pinout, okay, it will show you all the pins. And I like to check the data bus. For, the data bus be 0 to 7 or 1 to 8, depending how they number it. And the address bus. I will check every pin all the way across. And if any of those pins are stuck, we have a problem. Okay. And then the next thing that I like to test, let's say that tested good, I like to test the buffers. Now, you can look up in your schematic, what a buffer is going to do is it's going to have the data from one of these pins goes into a buffer and comes back out, or the other way around, okay? And often buffers fail. And so I will test the in and out of buffers. Now, you can look up the pinouts for these buffers online. Now, since we have, now that's just a quick and dirty, okay, what am I looking at kind of thing, right? Well, since we have this probe, how do we know if what we're testing, see, you know what, let me explain it this way. Often you're in trouble if you don't have a pulse. But sometimes things are supposed to not have a pulse until something happens, another event happens later. So how do we know when something is supposed to be pulsing and when something is not supposed to be pulsing? Well, for example, let's just make up an imaginary chip. Okay, we're going to touch that imaginary chip. Now, if you understand your logic gates, you will look at that chip, and then you can look at it in the schematic and go back, and depending on what the schematic says, you can actually trace it back to its source, to a source of why it's pulsing. Okay, and then see, maybe that is the thump for asteroids. Well, the game's not playing, so it can't make a pulse at the thump, or something like that. Okay, well, in order to be able to trace it back to see what is going on, you need to know your logic gates. So, my wife printed out some pictures here for me. We're out of black ink on the printer, so she printed it out in blue ink. Let me adjust the camera here. let me explain some simple logic gates so we know what we're doing. Now, let me get something to write with. When you're looking at those chips, let's say it looks something like that. And we have a NOT gate, so there's going to be, I think, there's going to be NOT gates that come in through, let's call this a 74 LSO4. What's going to happen is there's going to be, let me zoom in, is that too far out? Okay. In that chip, this symbol stands for something. And if you look at the pinout of specific chips, you will see all types of different symbols. What we want to know is, what the hell do these symbols do? Once we understand what these symbols do, we can understand how a chip actually functions. Okay? Now, for example, this gate is called a NOT gate. Okay? Now, if you'd like, you can make a truth table, what's called a truth table. Okay? And on the left-hand side, we can put all the possible inputs. And on the right side, we can put all the possible outputs. Now, what a NOT does is it actually inverts. For example, the 74 LSO4 here, my imaginary 74 LSO4, is called a hex inverter. Now, hex means there's 6 inverters in one chip. Okay? So, what happens is, I'm going to refer to things as on. I'm going to refer to things as off. I'm going to refer to signals as 1. I'm going to refer to things as 0. Okay? And what all that means is, does it have 5 volts or does it have no voltage? Okay? So, imagine this is a wire. Imagine this is a wire. If I were to get my probe would show that I have a voltage. And if I were to go over here where it's off or where it's 0, my probe would show I have no voltage. Okay? So what a NOT gate does is it inverts. Remember, it's called an inverter. It will invert a signal from one type to another. The only types we have are 0s and 1s. Okay? So for example, if our input was a 1, our output will be a 0 because it's been inverted. And the same thing, if our input had 5 volts, our output's going to be a ground. If our input is on, our output will be off. Okay? So, I know I have terrible handwriting, you know, enjoy. But, so that is super simple, right? But, now that we understand what this is, we can, for example, usually around the clock circuit, right here. Here is a 74 LSO4 chip on this board, okay? Now, since we understand what this gate does, we can now understand exactly what this entire chip does. So now we have a complete understanding of how this chip works, which is great. But there's a lot more chips to go through. So there's a lot more to learn. Okay, so we're going to talk about you know what, NAND. Let's try to find AND before we go NAND, huh? Okay, here. Now we have an OR gate. Okay. Now we can look at our truth table here and see we have 2 possible inputs. Now we have 2 inputs and 1 output. Okay. Now here are our possibilities. Both can be off. Okay. And if that's the case, our output will also be off. Okay. Now we still have 2 inputs. One could be off. One input could be on. Okay, now we do have an output. Remember, this is called an OR gate. So, if this input or this input is on, then our output will be on. And, you know, since this or this is on, example, we have both on, the output is still on. Does that make sense? So there are entire chips where they are filled with nothing but OR gates. You might have 4 OR gates inside one chip. And so now we understand what that entire chip does. Okay, so for example, the first one, that chip was filled with nothing but NOT gates. And what is this, 32 or something? Or is that the AND? Whatever. Okay. Yeah, we can talk about NOR. Okay, so now we have a NOR gate. Now remember how our NOT gate has this little circle? Well, this circle is reused into a lot of other gates. And what the circle really means is that whatever is going through here will be inverted. Okay? So, we have a tiny circle. You may not be able to see it in camera. But all we have is an OR gate. An OR gate just like this. But we have added a circle to the end. Okay? So, all the same rules apply to a NOR gate as an OR gate, except the output will be flipped. Does that make sense? So for example, if we have, let's say you have one input is a 1. For example, I can put a 1 here. And the other input is a 0. Since this is an OR gate, it will turn on the output depending on, if one of these is active. But then it's inverted. So this is actually a 0 output. Okay? This is a standard OR gate which has inverted output. Okay, what do we got here? XOR. Yeah, we can talk about XOR. Okay. Now, with XOR, there is one condition that is different with XOR compared to a standard OR gate. Now, remember how we had our OR gate right here. And remember how if both inputs are high, the output is high? Well, with an XOR, if both inputs are high, the output is low. Okay? Besides that, it's exactly the same thing. So it excludes one specific type of input and changes it. Okay? Now, keep in mind, all these different gates we're talking about are inside these chips. Once we understand what these gates do, we can, well, there's a lot more to it than that, but we're going to stay basic. We can understand what many chips do, okay? XNOR, same thing as an XOR, but we inverted the output, okay? That's all that is. You get it? Now, AND gate. Probably should have done this early. But here you have an AND gate. Now keep in mind, the names of the gates give us clues on what the gates actually do. Okay? So, for example, we have one input. We have a second input. We have one output. Okay? Now, if this input is a 1, we have no output. If this input is a 1, we still have no output. But if this input and that output are both 1s, then we will finally have an output. Does that make sense? Now we're at the NAND gate. Guess what? The NAND gate is just an AND gate that has an inverted output. Boom! Okay, so I printed out some random chips. Okay? Now, this is going to be our imaginary circuit board. Now, to explain this, VCC is on most of these chips, of course. VCC is actually going to be your connection to the 5-volt rail. And ground, you guessed it, ground is going to connect to ground. Okay? Now, for many of these chips, that's all you need to power the chip. Okay? So, since we know what some of these gates do, we can diagnose what the output would be. And if we know what the output should be, we know if that circuit's acting correctly or if it's not acting correctly. For example, we have a 1 and a 1 going to an AND gate. Remember that if this and this input is a 1, then the output will be a 1. Okay, so we're going to follow our imaginary circuit board trace over to this OR gate. Now remember, if this input or this input is a 1, then the output will be a 1. Okay, so we're going to follow our imaginary circuit board trace to this guy. Now remember, if this and this are a 1, this will be a 0. So we can follow this to our imaginary chip over here, which will invert the 0 to a 1. Now, when you have your logic probe set to ground, power to ground and power to your VCC, you will be able to see what these pins are doing. Okay, so for example, let's say your output is a 1, but this is a 1 and this is a 0. We know something's wrong. Okay, and so because we know that this can't be a 1 and this can't be a 0 if this is acting improperly. So what we can do is we can trace the circuit back and say, okay, well, I know what this part does. Is this part working right? And we can verify it. When you touch the probe, it'll tell you what it's supposed to be. We can trace that section back. We can verify this. Okay, this is supposed to be this because that's what that gate's designed to do, but it's not doing that, or it is doing that, etc. Okay, so that's why it's important to know at the early level how the gates work and what they do, because once you understand the simplicity of this, then you can go on to more advanced things. Okay. Here is a sort of a game that you can play to help you understand on the fly how these circuits work. Now these are very simple. This is very introductory. Okay, but let's say you have an imaginary computer. Okay, and your imaginary computer has 4 switchable lines. Okay, now on this bus, which is a grouping of wires, on this bus you can have any of these inputs or any of these outputs be a 0 or a 1. Okay, now let's add a couple more. Let's make this even more complicated. All of these lines can be switched from 0 to 1. Okay, well, let's say you want one specific command, only one command, not several, just one command to equal a 1 on this line. And let's say you have to start with 1 1 0 0 1 1 0. Just some made up code, right? Now, if you want this to become a 1, you can fill in all the gates that would make this be a 1 only under this specific condition. Okay? And you can do that kind of as a game. So in other words, when this and this are 1s, we can probably put an AND gate here. Okay? There's a little AND gate. And we know that this and this must be a 0, so we can put a NAND gate here. And we know that this and this would be another AND gate. And this could be an inverter. We can leave that alone. But you can fill in all these things. And just as a game, use your gates to make this become a 1 only under this circumstance. Does that make sense? I don't know. Maybe you can make a game out of it to help learn. Okay, so what do all these 0s and 1s mean? Well, the right combination of 0s and 1s, or binary code, can trigger certain actions on a circuit board, and they can actually be directly related to specific numbers. Okay, so let me explain binary code. But before I explain binary code, let me explain why we have to use it. Okay? Now, for us humans, it's pretty easy to understand our base 10 number system. For example, we have exactly 10 numbers, 0 through 9. And we can repeat those same numbers to make multiple numbers. Okay? Well, a computer does not exactly understand 0 through 9. A computer only understands the presence or absence of a voltage. So we have to make a special code to make zeros and ones equal numbers. Okay, remember how I mentioned our imaginary computer that could spit out all kinds of different data? Okay? And those could be zeros and ones and zeros and so on, right? Well, in binary code, this combination of zeros and ones actually are equivalent to specific numbers. And the way to tell is if you were to put it in this chart here, okay? Now, let's say here we have a 0. Let's say here we have a 1. Let's say here we have a 0. And let's say here we have a 1. Okay? So, we know since these zeros and ones line up with this chart here, and this chart goes on forever. It could be 16, 32, 64, 128, 256, 512, 1024, 2048, and so on. Okay? And all it is doubling. Okay? Now, if a 1 lines up here, we can add 2. And if a 1 lines up to this 8, we can add the 8. So 8 plus 2. So this number is 10 in binary. So why would we need to know what different numbers are? Well, there's a million reasons. But let me go with a very simple example. Often there are chips on circuit boards called counters, and counters often fail. And so let me just make a simple example of how a counter operates. And so once you understand how it operates, you can understand if it's operating properly or not. Okay? So let's make our imaginary chip. Okay? And there's our chip here, and let's have some inputs. We're going to call these inputs A, B, C, D, and we're going to have some outputs. These are flip-flops internally here. So we're going to call this QA, QB, I'm sorry about my handwriting, and QD. Okay? Now, we're going to have a pin right here. We're just going to call this, we're going to make up a name. We're going to call this pin carryover. How about that? That's our carryover pin. Okay? And there is other pins, and we're not going to go into full depth of what they do. But let's just have one more imaginary pin. We're going to call this pin clock. Now, a clock in an electronic circuit is nothing more than a pulse. It's that 1 and 0. It's that on and off, turning on and off, making a pulse so a counter can work. Okay. Now, this A, B, and C can take binary code. We'll go into this. If you leave these with no inputs at all, the counter will start at 0. If you were to if you were to add some code over here, add a specific number. Let's say you put in 4. This counter will start counting at 4. What does a counter do? It counts. Okay? So, if we were to start the clock, it would start at 1, 0. Oops, I put it 1, 0, 0, 0. And if we were to hit that, excuse me, if we were to hit the clock line again, we will get 0, 1, 0, 0, and so on. It will count, and you can convert that output into something that we can understand. Does that make sense? Oh, and if we get to the highest point this counter can count, this pin can be activated to control yet another counter. So this can be connected to the clock right here of yet another counter to count even larger numbers. Does that make sense? Now, let's say you only want this counter to count to 2. Okay? Well, you can actually, there's a reset. Well, let's say another imaginary pin. You can connect it right to there. So it'll count 1, 2, 1, 2, 1, 2, 1, 2. Now, most people will tell you that the only tool you need is right here. And I disagree. I highly disagree. Why? Why would I disagree? Well, let's say, for example, your clock circuit. Remember how we just talked about counters? Well, counters are often used to divide a clock circuit. For example, on this Asteroids PCB, we have a 12.096 megahertz clock. Okay? Now that is being divided to different frequencies across the board. And the CPU definitely does not run at a clock that high, so it must be divided down. Well, often on PCBs, there will be a terminal. For example, when this is divided by 2, this clock, it becomes 6 megahertz. Okay. Now, if we were to check this, we would, and if we were to see a pulse, we can assume that, okay, it's good. But we don't know. This counter, wherever it is, could be malfunctioning, and it could be at 3 megahertz or whatever, which would throw the whole board out of whack. So, how do you find out frequencies? Well, you need a scope. And I will tell you something else. Let's say you find in an output that is not truly 5 volts-ish. See, the logic, there's TTL logic in here. You know, we always say it's 5 volts, but it's usually a little less than 5 volts that actually triggers all these different gates. Well, let's say it's in a range where this will detect it and claim it's good. But if you were to look at it on a scope, you can see it's a weak output. Often this will lie to you, but a scope gives you a little more information so you can actually, detect it for yourself. So if you want to get into any repair, and especially vector repair, I suggest you get yourself a scope also. And not to mention, if you want to do vector repair, get yourself, and also not to mention, since I'm here, if you're going to work on vector games, I strongly advise you to get a scope with XY mode. Why? Because you can actually see, for example, on this Asteroids board, it has an X out and a Y out, and a scope has two probes, and you can set your scope to XY mode, and XY mode will emulate an actual vector. Well, it is a vector monitor. We'll show you a picture of the game playing on screen. How nice is that? Now, remember how I mentioned that game you could do to try to learn your gates with a imaginary bus from a computer? Okay. Well, remember how that bus is going to put out binary code? Well, you can use that binary code, once again, like we said, to associate to different numbers. Well, different numbers mean different things for different components. For example, let's make an imaginary EEPROM. I'm using that word a lot in this video, imaginary. But let's say we have an EEPROM. Okay? Now, the way an EEPROM works is you'll have address lines. And those can connect right to our bus. Let's say we want specific data to come out the data lines. And we know where it is. Well, the programmer knows where it's at. Okay? depending on the number or the combination of zeros and ones going through the address lines, we can access the addresses. Remember, this is called addresses. We can access exact sections of the data to come out of the EEPROM. Does that make sense? Anyways, this is just a super basic thing. Just to, this is for absolute beginners to just kind of some certain things to think about, and maybe this helps somebody, maybe this didn't. Keep in mind, I'm oversimplifying everything here, and yes, there's a way more in-depth way to explain all this, but that's not what you want, is it? I would hope not. If you're willing to watch this video, I'd imagine you're on the beginner level anyways. So, anyways, thanks for watching. Please subscribe to my channel, and have a good day, guys.